Hey everyone, and welcome to this explainer. Today, we're going to be translating the invisible language of maps. We're talking about turning you from a passive passenger into an active explorer and really unlocking the actual architecture of the Earth.
All right, let's just dive right in. I want to challenge something that, honestly, most of us do every single day without even thinking about it. Think about our modern reliance on that pulsing blue dot on our GPS apps. We follow those turn-by-turn instructions with, a kind of passive obedience, don't we? But that consumer-grade simplicity, it often totally obscures the deeper spatial relationships of the world right around us. Sure, it tells us where to turn, but it absolutely doesn't tell us how the environment is actually stitched together.
So to move beyond that blue dot, we really need what's called spatial literacy. This is the ability to decode a map not just as a literal picture, but as a purposeful abstraction of physical reality. And true spatial literacy? It's an absolutely mandatory competency for professional strategists and planners. It essentially gives you a God's-eye view of environmental constraints, allowing you to take all this complex data and synthesize it into a structured, professional language.
But before we can even begin to read that language, we have to accept a pretty fundamental cartographic truth. Every single map is an honest lie. And why is that? Well, it's because of the orange peel effect. Think about it, it is physically impossible to flatten a three-dimensional sphere onto a two-dimensional flat surface without tearing or stretching it. Literally, just like peeling an orange, you can't lay the skin completely flat without making a total mess, or in a map's case, breaking the proportions. Because of this, every map has to distort either shape, area, or distance. It can just never preserve all three perfectly.
Moving right into Section 1, the magic of scale, the universal translator.
Now, scale acts as that universal translator between the map in your hand and the actual ground under your boots. There are a few different ways to express this, but they definitely aren't all created equal. Take a statement scale, for example. Something like 1 centimeter represents 1 kilometer. Great for quick verbal communication, right? But it becomes dangerously inaccurate if that map gets photocopied or digitally resized. That's why when scoping out multi-million-dollar projects, professionals rely on the much more resilient linear or bar scale. Because it's a physical line printed right there on the page, it scales proportionally with the image, so it maintains its ground truth integrity whether you zoom way in on a screen or photocopy it from an A4 to an A3 piece of paper. It's pretty foolproof.
To actually translate that flat map into physical logistics, we use a beautifully simple formula. Actual distance equals the map distance multiplied by the scale. Honestly, this is your primary safeguard against massive procurement and logistical errors.
Let's put our planner hats on for a second here. Say you're using a representative fraction, or RF, of 1 to 50,000. What that means is 1 unit on the map equals 50,000 of those exact same units on the ground. So you're out in the field and you measure exactly 4 centimeters between 2 proposed infrastructure points on your map. What does that mean for your budget? Well, you simply take that 4 and multiply it by 50,000. That quick bit of math gives us 200,000 centimeters. And when we convert that, bingo! It perfectly translates to exactly 2 kilometers of real-world distance. By knowing this ground truth, planners can accurately estimate materials, pipeline costs, and transportation logistics way before they ever deploy a single field team.
All right, Section 2, decoding the 3D landscape, contour lines.
These imaginary contour lines, which connect points of equal elevation, literally dictate the feasibility of your entire project. By analyzing how they're spaced, we can unlock all sorts of hidden risks. For instance, steep slopes look kind of like a compressed spring on the map, and that's a huge warning of high cut and fill costs. Gentle slopes, where the lines wander far apart, well, that signals prime development land. A concave slope looks almost like a bowl, warning planners of heavy drainage requirements. And convex slopes? Those are wide at the top and dangerously tight at the bottom. They scream high landslide potential, which is going to require massive geotechnical interventions.
Now, beyond just the contour lines, maps also use this universal visual shorthand to help you quickly digest the landscape. It's a color palette that categorizes the natural world at a single glance. Blue, as you might guess, immediately identifies water bodies and drainage systems. Brown warns of rugged terrain, mountains, and high elevations. And green highlights lowlands and fertile, vegetated zones. This is absolutely crucial because it ensures a surveyor, an engineer, and a planner can all look at the exact same document and instantly understand the physical barriers and resource flows without missing a beat.
Moving on to Section 3, navigating the grid, precision localization.
To find a single specific location on a massed planet, we rely on an intersecting web of numbers and letters. But let's be real, reading coordinates can sometimes be notoriously counterintuitive.
That's exactly why generations of professionals use this highly memorable little rule: along the corridor and up the stairs. It's simple, but it ensures you always read your horizontal progress along the bottom first. Those are known as eastings, followed by the vertical climb up the side, which are your northings.
And just how precise you need to be determines the type of reference you're going to use. For example, a 4-figure reference gets you to the right neighborhood, basically identifying a 1 square kilometer area. That's perfect for something like regional zoning or mapping out a massive forest. But if you need to find a specific desert well, or say rescue a stranded hiker, you absolutely need the military-grade precision of a 6-figure reference. That dials the location right down to a highly specific 100-meter square.
And finally, Section 4, the modern geospatial stack, digital cartography.
So modern professionals don't just abandon these foundational analog skills we've been talking about. Instead, they integrate them with high-tech digital systems like GIS, real-time GPS, and remote sensing satellites. But because a printed map is ultimately just a frozen snapshot in time, obsolescence is kind of your biggest liability here. To avoid total disaster, modern strategists rely on a pretty rigorous 3-step framework. First, mandating regular updates to account for rapid urban change. Second, cross-verifying legacy paper records against fresh satellite intel. And third, enforcing standardized training to eliminate human error when reading complex scales and 3D contours.
When you really master this language, it completely transforms your perception of the world. You no longer just see a path to a destination, you actually see the personality of the land itself. So the next time you open up a navigation app, I challenge you to look past that pulsing blue dot and ask yourself, are you just a passive passenger mindlessly following a line? Or are you an active explorer? What deeper architectural language of the Earth are you missing right in your own neighborhood? Keep exploring, and thanks for joining me on this explainer.